My name is Jeremy Boone. I work at Research in Motion, and I'm here to talk to you today about some of the fuzzing activities that goes on for BlackBerry and Playbook products. So some background on myself and the team. So I lead a team called the Automated Code Analysis team within the BlackBerry security group. We support various activities of the secure development lifecycle. So that usually manifests in research and development, in security automation tools, largely fuzzing and static code analysis. But we also provide guidance to dev teams in the form of presentations or papers or just one-on-one sessions so they can understand what we're doing and why it's important. So what I'm going to talk about today, so we have this fuzzing framework that we call ALF. So I'm going to overview the ALF goals, talk about the overall framework's architecture, and then do some deep dives into some things that I think are interesting and hopefully you'll find interesting as well. So with ALF, one of the biggest things for us was about making fuzzing more accessible. A lot of developers and testers, and I'm sure this is true across the whole industry, are intimidated by security. They hear the word security and they back away. So we like to transform security problems into regular quality problems. When they're triaging crash reports, they're just crash reports and not necessarily security incidents where you have to throw your hands in the air and panic. We like to take the pain out of fuzzing as well. When our fuzzing framework was born out of a couple independent fuzzing systems that we recognized the commonalities between, and we kind of glued together one cohesive system. And I imagine a lot of people in this room have done similar things. And when people are fuzzing at RIM in the dev teams or in the security group itself, we would like for them to get running as fast as possible. So we provide a lot of the common tools that you use when building a fuzzer out of the box. I'll talk about some of those in a minute. And one of the last goal of ALF is fuzzing at scale. So this is kind of a clunky box diagram of what our fuzzing architecture looks like. You can see the 3 columns along the top, monitoring, instrumentation, and mutation. These are things you're probably all familiar with. You can't have a fuzzer without having these 3 things. If you can't monitor your target for crashes, then you're going nowhere. If you can't instrument and speak to your target, then you're going nowhere. And if you can't mutate the inputs to your target, then you're going nowhere. When someone is building a fuzzer within ALF, they could say, okay, I want to debug with GDB, call this API, attach to my target, done. And we also have other monitoring interfaces. With instrumentation, I'll talk about that a little more in a moment. On the client-side framework, we have minimization, exploitability classification, and then the server-side framework. So one server talks to many clients. And on the server side, things that might look familiar, crash bucketing via hashing of the stack traces, that kind of stuff. So I'm going to dive into a few areas in this diagram and talk about some of the specifics, why we made certain decisions, and maybe you guys can benefit from this as well. Mike Eddington told me once that every security person has a fuzzing framework inside of them somewhere. That's where that quote came from. I don't know if it's his or not, but this is what ours looks like. Oh, I also love Nyan Cat, so. So, deep diving into a few pieces of ALF. I want to talk about our virtual machines and our distribution model. So that touches the following, the highlighted components on my chart there. So in the interaction and layer, the VMs, the ALF client framework itself, the server communications, and on the server side, the client communications. We also do some health monitoring and package plugin management. And I'll explain these now. So the way the clients communicate with the server is really simple. Just HTTP, GET, and POST. Web servers are designed to scale, so why don't we just use that idea again? We don't need to roll our own here, and this helped us scale ALF to the size that it is today. We also support sending of custom commands, so the server can tell the client to shut up for a little while, stop sending me results, I'm going to tell you what to do in a minute, or simply restart yourself. These things are useful if some of the clients are going off the rails and you want to tell them to pause while you're debugging, or just restart, because sometimes flipping the VM is a good quick solution. We can also push down software updates if we update our mutation engines or something like that. And then, of course, the fuzzing units itself. The server pushes to the client a package and says, here's the program that you're to fuzz. Here is the scripts that wrap it that you're to fuzz it with, and do it for this long. And then when the client is done, it sends back its results, of course, and some general system health, like my disk space shows that I have this much free memory, or I have a few processes running that I was unable to terminate. And we use information like that over time to decide whether we want to kill a VM because there's something wrong with it. So our cluster. So we have about 100 servers spread across a few IT labs at RIM. Each server runs a few VMs, nets out to about 400 plus for the 100 servers. Each of those VMs is multiprocessing all of its mutations, and in total we're achieving about 100 million iterations a day. This varies wildly. Some things that we're testing take minutes to run a single test case, whereas others you can run hundreds of test cases in a second. So depending which fuzzers we've chosen to prioritize at that particular time, this number will jump up or down. So why are we using virtual machines? I've touched on this before, but basically fuzzing is destructive. You guys have probably seen your OS crash while fuzzing before. And that's not uncommon. And we don't want, when we have to deal with 400 virtual machines, we don't want to play sysadmin and log in manually and repair things. So with a VM, we could just hit the reset button and we're good to go. It takes a lot of pain out of it for us. So some of the challenges. ALF runs in a lot of different environments based on the particular thing that we're fuzzing. Making it behave the same across all of them can be tough. We're benefited here because ALF is built in Python, so that does give us some cross-platform advantages, but there's always gotchas. So it's always something for us to be aware of, not to mention the fact that debugging in different environments can affect things. Maintaining a healthy cluster. Clients will drop off the grid, they'll deadlock, we'll have memory leaks, the underlying OS may crash. So one of the best things for us sometimes is just to restart the VM. And human error as well. Sometimes when we write a new plugin for ALF and we push it out to our 400 VMs and say go, if there's a bug in that and all of those VMs drop off the cluster at the same time, we have a really bad day. So we're really cautious of things like that. So scaling up a fuzzing rig like this, there are huge benefits, but there's a lot of things that you have to be aware of. So regression testing. So because we're on RIM has products and we're not just fuzzing for O days, we want to improve not just the security but the quality of RIM's products. We have a regression functionality built into ALF. And this is something that really helps developers. Pretty straightforward, so ALF finds a bunch of crashes, developers fix them, integration rolls a new build, we update that build in ALF and replay our regression suite. So we rerun every single crash we've ever seen before. And that's not just buckets of crashes or unique crash signatures, but every single input that's ever caused a crash. And we do that because we recognize that there may be subtle variance between those, that even though at one point in time they converged and caused the same bug, if that bug was fixed and you play them again, they may hit different bugs later, or one of them may. So we have to pay close attention to the output of our regression suite. So a lot of questions arise, like what do you do if the stack trace changes? Just the major hash or the minor hash changes? What do you do if the class of exception changes? Or if a previously fixed crash has reappeared? Or a crash that shouldn't have been fixed mysteriously disappeared? Or if you have lots of different crashes in the same bucket, like the diagram on the right illustrates, where they're all converging on that red function call where the defect exists. That's the same bug, even though there's many ways to get there. A developer may not patch it at the right place. He may only patch one of the code paths. So, I mean, how do you handle that in an automated way? Because our goal here is to make the process of fuzzing as simple and painless as possible. And we don't want developers to have to sort out these dependencies automatically. So, therefore, we have to be intelligent in our decision making. We have to pay attention to the full history of any input to ALF and how things change. I can tell you that every single crash matters, so the last thing we want is to accidentally toss something away if we think it's too closely related to another bug. Accidentally, I mean. A lot of people talk about fuzzing just for memory corruption bugs. I find this concept interesting, fuzzing a target and looking for a bug that can't be revealed through attaching a debugger and waiting for the process to crash. It's a tough problem to solve, and Jesse is laughing there, so I think he might agree with me. But also, when you're fuzzing defensively, every single bug matters. We're not here to write exploits for these bugs. We're here to fix them to make the quality of the product better. So every single bug that we find. And a timeout bug, like say an infinite loop in some piece of critical infrastructure, is really, really important. Probably more important than a null pointer dereference or something more benign, but still resulting in a crash like that. So how do we deal with timeout bugs? A lot of people in their fuzzers say, well, we'll just run this thing for 30 seconds or a minute, or at some point we'll cut it off and say enough is enough. But we wanted a way to get more reliable information than that, because if you cut off the execution after a certain period of time, the stack trace could vary wildly from run to run, even for the same bug. So if you look at the call tree diagram I have there, so the function highlighted in red that contains the infinite loop calls A, B, C, and D, which then call many functions. And if you're just killing it at a random point, you could be executing inside any of those functions inside the while loop. So your stack hashing is kind of thrown out the window at that point. So we wanted a more reliable way of bucketing these bugs so we could give a cohesive report to a developer and say this input results in this infinite loop. So what do we do? First, we run the base template against the target. This is the unmutated kind of raw input. This doesn't work if you're doing generational fuzzing, but file fuzzing is a lot better for this. So you measure how long it takes to run the base template, and that's your baseline. So you'd assume that any mutations to that should run in about the same time. The reason why we need to do this is because, say, if you're fuzzing a media player and you just say, well, 1 minute is enough, but you play an MP3 file that's 90 seconds long, then you're going to cut it off early every time. So it has to be proportional to the baseline runtime. Build in a fudge factor, just because you can't avoid that, because we're multiprocessing on these machines. So if we run longer than the baseline times the fudge factor, then we halt, and then we run it again, this time with pin, instrumenting everything as it's executing. And so we're recording every basic block that we're hitting. And we stop instrumenting with pin when we see that we're not hitting any new basic blocks anymore. So at that point, we can assume we're probably stuck inside that while true loop, and we're just hitting the same things over and over and over again. At that point, we stop instrumentation with pin. We split the stack trace along the line where we believe the infinite loop begins and everything before it. And it's usually easy to tell heuristically because the things inside the loop will have, orders of magnitude more executions than the things leading into the loop. And then you hash everything leading into that infinite loop condition. And that's your unique fingerprint for this bug. So basically, you're treating that while true condition as the halting, or as the instruction that raises the exception if you were looking for a crash, in other words. And this works pretty well. In some of our timeout buckets, in one product in particular, we were seeing thousands of timeouts because our bucketing was bad. And after implementing this, it shrunk it all down to about 10. So QEMU. So why do we use QEMU? Well, it kind of makes us feel like a badass, first of all. But there are times when you have to use it. A lot of RIM products run inside a VM, a simulator. So we have a simulator for Playbook, for example. But that doesn't work if you want to fuzz something that's deep inside the system and you want to isolate just that component and fuzz it. And so you kind of need to pull it out and run it inside an ARM emulator. The other thing is that sometimes the differences between ARM and x86 matter. So our Playbook VMs are x86, but the product is built for ARM platform. So pieces deep within the kernel, graphics drivers are heavily architectural dependent. There's such a thing as ARM Neon, which is an optimized instruction set for ARM processors. So, these are examples where we have to use QEMU.
You ever try to fuzz to find differences between QEMU and real ARM?
No, but that's a really cool concept. Yeah. So when you're doing this, there are things you have to pay attention to. So if you're reaching deep inside the architecture and pulling out one piece of a driver, and you're saying, okay, I want to fuzz that, you really have to understand what the threat model or the attack surface is for this component. Is this a realistic attack if the way the system is architected, that there's 10 layers of defense that sanitize inputs? Or if this is a low privileged application, or if it has so many dependencies that it's just not realistic to stub them all in order to run it in such a minimal environment like QEMU. And sometimes one of the hardest things is just getting the frigging thing to compile. So that's it. I think I'm close on time. Hopefully some of this was useful to you guys. The big goal of what we're doing here is trying to make fuzzing as simple and painless as possible for developers, so that, as I said before, we transform a really intimidating security problem into a much more simpler problem of quality. Thanks a lot. Certainly.